Hello everyone, my name is Artur Dovbysh and today I'm gonna present you our work on the following topic: performance evaluation and analysis with code benchmarking and generative AI. So yeah, let's move forward. Let me shortly introduce the content. This work explores code benchmarking techniques and their integration with advanced generative artificial intelligence models, emphasizing the need for continuous performance optimization in data-driven industries. Benchmarking is essential for evaluating and comparing hardware and software performance, identifying bottlenecks, and developing improvement strategies for any software product. This study reviews benchmarking theory and practice, detailing key parameters, steps, challenges, and solutions for researchers and practitioners. For the sake of an experiment, our work examines benchmarks for various sorting algorithms. Innovatively, the study uses AI models like GPT 3.5 Turbo and Gemini 1.5 Pro to analyze raw algorithm benchmarks, categorizing efficiency and redefining performance evaluation. The effectiveness of this approach is assessed using the F-score metric, providing insights into AI model performance. As a result, we expect this research demonstrates the potential of integrating benchmarking techniques with generative AI, marking a significant advancement in automated code analysis and offering valuable implications for software development and AI applications. So let's begin. So you may ask why benchmarking is important. Here we emphasize the following points. The first one is optimizing resource utilization. Efficient code ensures optimal use of hardware and software resources, reducing operations cost and energy consumption, which is crucial for both economic and environmental sustainability. Enhancing user experience also. Faster and more responsive applications lead to a better user experience, increasing customer satisfaction and retention. Performance benchmarking helps identify and eliminate bottlenecks that can degrade application performance. The following topic is improving scalability. So benchmarking allows developers to understand how their applications perform under various loads, ensuring that systems can scale effectively to handle increased demand without compromising performance. Ensuring reliability and stability through systematic performance evaluation, benchmarking helps in detecting and resolving potential issues that could lead to system failures, thus enhancing the overall reliability and stability of application. So, and if to sum up, performance testing and benchmarking are critical aspects in development process of systems, applications, and networks. They serve fundamental roles in ensuring that these digital assets meet their intended functionality and service quality. Performance testing is a methodical practice that helps developers examine how a system behaves or responds under different circumstances, including workload, operational speed, and stability thresholds. It can help identify bottlenecks, understand system limitations, and confirm whether a system can meet its expected performance criteria. And ultimately, the combination of performance testing and benchmarking form a basis for delivering superior quality products, which is very important nowadays. Why AI? Well, basically, one of the main problems we faced and continue facing in modern work with benchmarks is the fact that many people simply do not understand how to work with these metrics. This is it. Programmers can easily write and carry out appropriate performance measurements in the form of benchmarks. However, they usually do not know how to work with this data. In addition, even if they can handle benchmark outputs, they easily can make a mistake during the analysis only due to a human factor. So basically, there are a lot of data, and you need to always remember about it. And the last but not least, it's time. AI models is capable of doing heavy calculation extremely fast. And one of the tasks of this work is to check whether the modern artificial intelligence models is capable of doing such sort of tasks. So our experiment consists of the following steps. The first one, we decided to check it on some sort of algorithms because they're easy to implement, and we decided to take 10 sorting algorithm as a code base. Then we conduct a benchmark collection for each algorithm using various data sets of different sizes. And the following step is to select 2 AI models as a competitors and make them to perform collected raw benchmarking data analysis. Then we evaluate their effectiveness using the F-score, and the final step is to perform some sort of summary and make conclusions on whether the AI models are capable of working with raw benchmarking data. To verify AI models, we decided to select the following algorithms. So a little bit of additional explanation here. We decided to hide each algorithm behind some random algorithm code. You can see it on the algorithm code column. The reason for that is to make AI models work only with raw benchmarking data without any additional context about the algorithm essence. And as you can see, this algorithm pool varies from simple bubble sort to more complex radix sort, cube sort, and tree sort. And for the task of amazing algorithm benchmarks, we opted to utilize the benchmark.net library in conjunction with the corresponding algorithms executed using the C# language. Why? Because this is my primary programming language, and it's just a question of ease of implement. This performance was guided by my past experience, as I said before, as a .NET developer. And we set up 3 iterations of tests. Each of this iteration consists of arrays of various sizes represented by the variable n, and all of this n is like 3 different cases where we have n set to 100, 10,000, and 200,000 of elements, respectively. So let's move to the experiment results itself. Okay, here you can see benchmark results of 100 elements array. Just need to be mentioned that before each iteration, we randomly generate each of these elements, and it also takes time, but this time is not included to the resulting calculation. We measure this matrix in uniseconds. The explanation of unisecond you can see on the title, and this the results are pretty clear. As for me, you can see the table consists of each algorithm code, size, mean, standard deviation, median calculated using benchmark process. And just to give you a short insight on it, the mean execution time ranges from 35.78 uniseconds to 428.81 uniseconds. Algorithm T3, which is quick sort, has the lowest mean execution time, while T8 has the highest mean execution time. That is expected. As far as cube sort, it's T9. has its own complexity issues, which are very visible on small datasets. It should be more efficient on bigger datasets. The standard deviation of execution times ranges to 106.47 uniseconds to 1081.19 uniseconds. T3, which is quicksort, I recall you, has the lowest standard deviation, while T9, which is kubesort, has the highest. Interestingly, even algorithm labeled as inefficient demonstrate satisfactory performance with small datasets, which is expected. Even bubble sort, which is T1, and selection sort, which is T2, were quite efficient on such small distance. And as you can see from the data we obtained, they are among top 5 according to the mean execution time. Let's move on to the next iteration of. Okay, here you can see results of the next iteration, which is 10,000 of elements array. It's a much bigger data set. And yeah, as you can see, things becoming more clear. Notably that bubble sort, selection sort, and insertion sort, which is T1, T2, and T5 respectively, shows that they are obviously inefficient certain algorithms. Conversely, proficient algorithms exhibit very good performance in execution times. As you can see, it is indicated by the mean execution time metric. The performance of kubesort, which is T9, presents quite bad, which is also expected. So we expected that our further investigation into the underlying factors contributing to these observed efficiencies could provide valuable insight into algorithmic optimization and computational efficiency. And finally, let's take a look on the last iteration of NX. Basically, benchmark results on this slide is collected based on the biggest data set, which is 200,000 elements array. Well, in this particular scenario, a very big workload is simulated for each algorithms. And yeah, just to provide you some context, you can see that now we clearly see which of the algorithms might be considered as efficient or inefficient. Overall, based on the benchmark results, T3, T8, and T6 appear to be the most efficient methods in terms of mean standard deviation and median execution times. So it's some sort of aggregated value. These methods consistently performs well in terms of speed and variability in execution time. In addition, T9, which is kubesort, finally showed its capabilities. This algorithm not as good as expected to be. However, it's much more better than obviously bad algorithms, which is T1, T2, and T5. And yeah, but it's only our analysis, and also just to recall you, we are aware of each algorithm complexity. And let's check whether the modern AI models are able to process raw benchmarking data, since not all the people know statistics and even fewer people knows how to analyze the data that we collected when measuring benchmarks. The help of AI models will be very appropriate. The task of the next slide to introduce you with the selected generative AI models. One of them is GPT 3.5 Turbo, developed by OpenAI, and the opposite one is Gemini, 1.5 Pro, which is developed by Google. Let me briefly describe each model. OpenAI's GPT 3.5 Turbo. GPT stands for Generalized Pre-trained Transformer. Is part of the third generation of large transformer-based language models with more than 175 billion parameters. It adheres to the auto-generative language model, which can process and generate text based on the preceding context. This model is often referred to as a chat model, as it's formatted to generate responses in a conversational context. The model is capable of, doing a lot of different stuff, including compromising emails, writing code, answering questions, creating written content, and much more capabilities. On the other hand, we have Gemini, which aims to leverage Google's Lambda, which is a language model for dialogue applications. Technology featuring capabilities in understanding and generating human-like text-based responses. This positions is as a competitor to other advanced AI models like GPT. Gemini is part of Google's broader effort to integrate advanced AI into everyday user interactions, helping to simplify everyday tasks, such as information retrieving, learning, and any other task you may imagine. So let's move to the result analysis. This table represents GPT-5 Turbo benchmarking analysis results. So just to describe you the whole process, we have attached all of these collected benchmarks we have shown you before using the CSV files to each of the model contexts. And there were like 4 different scenarios for each. In first scenario, we use benchmark output for 100 elements. The second scenario includes only file with results of 10,000 elements. The third scenario includes only results with 200,000 elements. And the fourth result includes all of available outputs we have received during this experiment. So the directive given to the model was something like that. Having attached benchmark files for 10 methods representing different algorithms to this chat context, could you please classify these methods as I, inefficient, or E, efficient? So please provide the answer in simple table format like T1, E, or T2, I, etc. Additionally, I kindly ask you to perform this evaluation 4 times, once using only the scenario number 1, scenario number 2, scenario number 3, and the fourth scenario will be including all of the files we have attached. So the model provides an output from to our conversational chat. Based on provided data, we can classify the algorithms as, and the results provided by the model you can see on the screen. Nothing to add, just a simple classification task were performed by GPT 3.5 Turbo based on raw benchmarking data. But how we can evaluate its correctness, effectiveness, because we are not sure each of these classification is correct based on our assumptions. And that's where F-score comes into play. Just as an example, how we calculate F-score metric, we decided to show you this slide with explanation of how we calculate F-score for GPT 3.5 Turbo outputs based on file with 100 elements answers. So the basic formula is where F1 is equal to 2 times PR divided by P plus R. where P is precision, is number of true positive results divided by number of all positive results, including those not identified that is not identified correctly. And its formula is shown on the right side. Recall, which is R, is the number of true positive results divided by the number of all samples that should have been identified as positive. And this formula, like TP, stands for true positive, and FP false positive. Also, we have false negatives, which is Fn, and using all of these inputs, let's proceed all these calculations. Using the table on the previous slide, we can easily identify that P, we can easily calculate the number of true positive and false positive, and calculate their precision, which is P. And also, using the same method, we calculating R, which is recall, and having two of these metrics, we can easily calculate the F-score. F-score in our scenario is 0.4, which is 40%. This is the slide with calculated F-score for each scenario, including all of the needed metrics. And based on these outputs, we can make a conclusion that the model is performing very well in correctly identifying both positives and negatives instances, with few false positives and false negatives cases. This high F-score in all context scenario, the last one, suggests strong overall performance and reliability of the model. Only in case of 100 elements array, model was not quite efficient. I assume the reason for that is that the dataset was quite tiny, to be honest. In addition, we must recall that models process only raw benchmarking data without any additional context of it. And I assume that such results are really nice and definitely states that AI model must be considered as a solution, as a solid option to be used in scenario of performance analysis. And now let's take a look on Gemini 1.5 Pro benchmarking analysis results. This table simply contains the answers. So here we have calculated F-score results of Gemini 1.5 Pro for each of the scenarios we tested. And Gemini models demonstrate consistent accuracy across all of the scenarios, which is great. We must admit that this model not only categorized all of our algorithms with the good F-score, which is almost 80% in general, but also provides its thoughts about algorithms. Something like it's like put it to the chat some thoughts like algorithms characterized by low standard deviation, such as T3 and T8, are deemed preferable when consistently in performance in general. On the other hand, algorithms like T4 and T7 might find applicability in niche scenarios where size input remains relatively modest. I assume that such insights are really helpful even in your everyday activity. And this model provides also great experience if to speak about classification using only raw benchmarking data. Also, I need to recall to the speakers that each of these models were consumed in a, let's say, raw format. because for such scenarios, if you want to achieve higher F-score and better results, better understanding, etc., you need to perform the process called fine-tuning for each model. But it's just an idea of how to improve this consumption scenario. And if to sum up, this experiment that we have conducted shows that artificial intelligence models can be considered viable tools to assist with our performance testing routines. Both models deliver impressive and accurate results without the need for model fine-tuning or consideration of additional context preparation. I'm sure that this field is should be explored deeply and developed further. Introducing fine-tuning for models will be a game changer. However, it's out of scope of this paperwork. Maybe in future iterations we will investigate it in more details. But basically, no matter which model you opt for, our investigation strongly points that with this with a proper preparation of inputs, we have a big potential to achieve even greater results in terms of code performance analysis. I just want to recall you that in my professional experience, not all developers fully grasp how to implement these methods, how to analyze the data, and that kind of stuff. And the models shows great precision over a broader range of scenarios. And potentially, we can achieve auto detection of problematic code based on trained model experience. This underlines a new possibility in how we approach and comprehend the effectiveness of efficiency of coding. The future of performance testing definitely stands with AI models. So by consuming the power of AI algorithms, developers can expect that paradigm will be shifted to some automated tools and other performance testing analysis environments. So basically that's it. Thank you a lot. If you have any additional questions or you want to clarify some details from this speech, please contact me directly via email. And special credits to my mentors, Vladyslav, Alieksieiev, and Anriy, Berko. Thank you and see you.